Hi, everybody. I'm going to answer a couple of the questions in the video because I think that's going to make a little bit more sense. So one of the questions was, how exactly do we end up getting this pi bond after the Diels-Alder reaction, considering the molecular orbital diagrams that we've been drawing out? So I just ahead of time drew out the molecular orbital diagrams for both the butadiene and ethylene. So these are the molecular orbital diagrams that pretty much cover all Diels-Alder reactions. They all go by this particular arrangement of orbitals, right? It's always going to be a butadiene of some kind and an ethylene of some kind, because it doesn't really matter what you have as substituents on here in terms of how the actual orbitals go together to form those bonds. So as we'll see in the next question that I'm going to address, sometimes the substituents can make a difference based on their orbitals, but the actual nitty-gritty of making the bonds for the Diels-Alder reaction just comes down to these two pieces. So it doesn't matter what substituents you have, they're always going to look like this. So if we start off with our molecular orbital diagrams, right, we're always going to be combining a HOMO and a LUMO. Probably the most common option is going to be the HOMO from the diene plus the LUMO from the dienophyte. I forgot to label these. Okay, so I'm going to do that one on the left. So I'm going to go ahead and make this my HOMO. So I've got one node here. And I'm just copying exactly what I have on my side 2 for the HOMO of my diene. Okay, so that's the HOMO of my diene. I'm going to match that up with the LUMO of my dienophyte. So whenever I'm doing this, I always make sure that the first side that I start with, I make it so that it's going to work out and match in the shading there. And then when you're really trying to see whether something is going to work or not, you'll see whether the other side also works, because you're always going to have either both of them are matching or only one of them is matching and one of them is not. You're never going to have an instance where neither of them can match, because that just means you just need to flip one of those to get your orbitals matching up. So it's always going to be both or just one. So to finish off this LUMO, we got that one node, and then we have our LUMO here. Okay, so we've talked a lot about how, these make our sigma bonds. So if we kind of draw that process out, which I really should have, let me pause this to get more space. All right, so once we have our HOMO-LUMO kind of combining onto each other with that positive overlap here, we're essentially are creating those sigma bonds, right? We talked about that a little bit. How we're overlapping those orbitals. Well, that got really ugly fast. Let me try this again. Okay, where we've got, this was our shaded overlap. This one was our white overlap. Okay, in the middle here, in this spot that it's kind of poorly drawn. And then in the back, we still have these two p orbitals, which haven't done anything. Okay, so these are going to turn into our new sigma bonds. And I'm actually going to try redrawing that because I just don't like the way that turned out. I'm going to draw them more as sp3 hybridized orbitals, and I think that'll look a little bit nicer. There we go. Okay, so we've got our new sigma bonds here. But what's going on back here, right? We've got two p orbitals that we essentially haven't touched. This is going to form your new pi bond. Okay, and it looks like they're forming like an antibonding orbital right now, but just keep in mind, every pi bond has to have an antibonding orbital and a bonding orbital, right? You have to have even numbers of those two things. So even though this one looks like an antibonding orbital, there is a bonding orbital that is going to be corresponding to that pi bond as well. Okay, so every pi bond needs a bonding and antibonding orbital. Okay, so this might provide us just kind of a snapshot of our antibonding orbital, but that doesn't mean that the bonding orbital doesn't exist as well. Okay, so if we just look at the other option where we took the LUMO of our diene and the HOMO of our dienophile. So let's go ahead and we're going to grab Psi3 for this one. And then the HOMO of the dienophile. So if we look at this option, once we make these bonds and form those into our new sigma bonds, right? Look what we have up here. This is just the other view of that lone pi bond that we're going to be forming, and that's going to form our new pi bond. Okay, so it's really just about like the fact that we have a couple of p orbitals that didn't get anything done to them, right? They're still p orbitals, they're still present. They did not turn into sigma bonds. And that's what allows us to have that p orbital in the final product and have that pi bond there. Okay. So this is from 2 leftover p orbitals that didn't participate in the reaction. And I'm going to specify that by forming sigma bonds. Okay. Because that's kind of the important part of the reaction participation. Okay, so that's all that happened. It's just we have 2 leftover p orbitals. They're still right next to each other. They're still going to have electron overlap and form that pi bond. Okay, so that's the first question about like where does that pi bond come from, and kind of putting it in a little bit of context with our sigma bond formation. So now we want to look at kind of a little bit more in depth in terms of how we look at the Diels-Alder reaction in combination with molecular orbitals. So one of the things that we have not discussed a ton, I've mentioned it a couple times in office hours, but this is going to be kind of like the big reveal of why we do things the way we do them. And I think that kind of getting some more context in the Diels-Alder reaction with molecular orbitals explains a lot about how we actually predict some of these products, because we've kind of been a little hand wavy about it in terms of like, oh yeah, you know, you set up your drawing tool like this, and you've got your dienophile, and you want to make sure that your electron withdrawing group is over the backside of the diene. And so we're doing this kind of thing. But we don't have a lot of context in terms of why we do it that way. But now that we know about molecular orbitals, we can answer that question, okay? So when I have a Diels-Alder reaction, it looks more like this, where I've got some electron withdrawing group there. We know from the question above that in order to determine the orbital overlap, I don't actually need to look at any of this, but it does help us to look at the orbitals in terms of explaining why we actually set up our drawing tool this way, okay? In terms of why am I overlapping that electron withdrawing group to here? Okay, and why don't I have it on the other side where it's not going to be like running into stuff? Okay, so to explain that, we really need to look at the molecular orbital diagram for our diene as well as our dienophile, including that electron withdrawing substituent. Okay, so in this case, they are both 1, 2, 3, 4, 1, 2, 3, 4. So they actually are going to have the same molecular orbital diagram because it doesn't matter that we've got an oxygen in there now. It's going to give us the same type of p orbital electron configuration that the butadiene does. Okay, so you can actually explain both of them with just this single electron molecular orbital configuration drawing. Okay, so essentially what we're going to do is we're going to use the same kind of HOMO-LUMO situation. So we're going to have the HOMO of our diene and the LUMO of our dienophile. So I'm going to go ahead and fill in the HOMO first. So again, I've got one node here, and it's going to be right there. And then for our LUMO, right, we're still using the same one. We're still using the 4 pi system. So our LUMO is going to be shaded there, and then the 2 nodes, one right here, and then there. Okay, so once we're looking at this, it's a little bit tough to see. I'm going to try to move this so we can see it a little bit more clearly. And I got my model kit too, because I anticipated that I was going to struggle drawing this, and I did. Let me try to fix it a tiny bit here. Okay, and the model kit will help explain it a little bit, I promise. Okay, so we have the normal bonding overlaps that we're expecting, right? Where we've got this forming a bond, that forming a bond. Those both overlap each other properly. So we're going to be able to do sigma bonds here. But it's actually going to be this orbital back here that dictates where exactly we are putting that that dienophile, okay, in terms of overlapping with the p orbitals over here. So it's actually going to see this interaction, and that's where we're going to overlap that. So it's a little bit hard for me to draw this because think about this is in the front, and then this one is going to hit here, right? It's just not, I'm not very good at drawing it, but I'll show you the model kit in a second. It'll make more sense. But this interaction is still a positive interaction. It's not actually going to form a bond, but it's going to help us kind of like a magnet draw that dienophile over so that that diene and that p orbital from your dienophile can just have kind of a nice positive little interaction there and lower the energy of that transition state. So if we take a look at the orbitals or the model kit real quick, I'm going to stop this share. So I've got my diene here, right? Just a simple diene. I've got it in my correct conformation here. So what we have going on here is we're choosing between this option, right, where I've got this way, right, where I've got the diene, the diene and the dienophile with the electron withdrawing group away from the diene. Okay, you see how the p orbitals that are here, they're going to be pretty much this, right? They're going to be in and out perpendicular to those bonds there, right here. Okay, so if I have the situation like this, where I've got an overlap here to make the bonds, but I don't have any way to overlap the p orbital over here. But if I rotate this, I'll try to show you this from a couple different angles. So if I rotate this, I can still overlap to form my bonds right here. But now you can see that I can also start to overlap this p orbital with this p orbital. Okay, so I'm going to try to line this up and then see what happens. So you see how this is being able to overlap right here. This one doesn't matter so much because it's sticking out pretty aggressively away, but just the fact that we can do this overlap between these two atoms while also getting those bonding overlaps between these four atoms, that is what's actually pulling our dienophile to be facing the backbone of that diene. Okay, so if we look at it from with the diene in the front, we can also do that. I don't know which one's better. It's hard on camera, but you can see how we've got this p orbital, that p orbital. Those are able to make that nice positive interaction there. So that's why we have, you know, that's one of the best explanations of molecular orbitals concerning the Diels-Alder reaction, because without the orbitals, we wouldn't have that really nice stereoselectivity that we benefit from a lot in the Diels-Alder reaction. And it's all because of that little interaction right there. So this interaction is good. So this is why we overlap the dienophile with the diene backbone for stereochemistry. Okay, so hopefully that kind of gives you a little bit better full context picture of the Diels-Alder reaction with molecular orbitals in all of its nitty-gritty details. So as always, let me know if you have any questions, and I will see you all later.